Hi, I'm Quinn, and today I want to talk about one of the weirdest phenomena in quantum mechanics: quantum tunneling. This is the thing that makes absolutely no sense when you first hear about it. Particles passing through solid barriers they shouldn't be able to cross. Like a tennis ball thrown at a wall and just appearing on the other side without breaking the wall. But here's what's wild. This isn't some far-out theory. This is happening around you right now. It's why the sun shines. It's why your USB drive can store data. It's why nuclear decay happens. So let's understand it through what physicists call the barrier problem. Let's explore the classical version of barrier problem first. Okay, here's the setup. The barrier problem. Imagine you have three regions of space. Region 1 on the left. Region 2 in the middle. That's your barrier, an area of higher energy. And region 3 on the right. Now you send a particle from the left traveling toward this barrier. The particle has some kinetic energy. Let's call it E. The barrier has a height. Let's call it V theta. The question is simple. What happens when the particle hits the barrier? Classically, if E is less than V theta, if the particle doesn't have enough energy to climb over the barrier, it bounces back. 100% of the time. It's like rolling a ball up a hill that's too steep. The ball doesn't make it over. It rolls back down. End of story. Now let's see the quantum version. In quantum computing, the barrier problem gives you a completely different answer. You solve the Schrödinger equation, the fundamental equation governing quantum particles, for this three-region setup. And what you get is shocking. Even when E is less than V theta, even when the particle definitely doesn't have enough energy classically, the math tells you there's a transmission coefficient, a probability that the particle makes it to region 3. Not by going over the barrier. Through it. Let me say that again. A particle with less energy than the barrier height has a non-zero probability of appearing on the other side of the barrier. This is quantum tunneling. And it's not a trick. It's what the math and experiments tell us happens. So what's going on in the barrier problem? In region 1, the particle is described by a wave function, a probability wave traveling toward the barrier. This is the incoming wave. When it hits the barrier at region 2, two things happen. First, most of the wave reflects back. This is the reflected wave. This part makes sense. The particle bounces off. But second, a portion of the wave penetrates into the barrier. And here's the key. Inside the barrier, the wave doesn't oscillate like a normal wave. It decays exponentially. It gets weaker and weaker the deeper it goes into the barrier. Think of it like sound waves hitting a thick wall. Most of the sound bounces back, but some of it penetrates into the wall, getting quieter and quieter as it goes deeper. Now, if the barrier is thin enough, even though the wave is very weak by the time it reaches the other side, there's still some wave amplitude left when it gets to region 3. And in region 3, that tiny bit of wave amplitude becomes a transmitted wave, oscillating again now on the other side of the barrier. The wave function in region 3 represents a probability that the particle is there. And if there's probability, then sometimes when you measure, the particle is there. The transmission probability, the chance of tunneling through, depends on what's happening inside that barrier. The wave function inside the barrier looks like this. It's exponentially decaying like e to the power minus or negative kappa x, where kappa depends on how much higher the barrier is than the particle's energy and how heavy the particle is. Three things control whether tunneling happens. 1. The barrier width. If the barrier is too thick, the wave completely dies out before reaching the other side. No tunneling. But if it's thin enough, maybe just a few nanometers, enough wave amplitude survives. 2. The barrier height relative to particle energy. The higher the barrier compared to the particle's energy, the faster the wave decays inside. Higher barriers mean less tunneling. 3. The particle's mass. Heavier particles have faster exponential decay. Electrons, super light, tunnel easily. Protons are harder. Something as heavy as a tennis ball. The decay is so absurdly fast that the probability becomes effectively zero. That's why you never see macroscopic objects tunneling through walls. Let me give you real numbers from the barrier problem. Say you have an electron with 5 electron volts of energy approaching a barrier that's 10 electron volts high and 1 nanometer wide. Classically, 0% chance of getting through. The electron doesn't have enough energy. Period. Quantum mechanically, you calculate the transmission coefficient and you get something like 13% probability of transmission. 13%. That's not a rounding error. That's a massive effect. Make the barrier thicker, say 2 nanometers instead of 1, and the probability drops dramatically. Maybe down to 1.7%. Make it 3 nanometers, 0.2%. It falls off exponentially with barrier thickness. That's the signature of quantum tunneling. The barrier problem isn't just a textbook exercise. It's literally how technology works. For example, scanning tunneling microscopes. You have a metal tip and a surface separated by a vacuum gap. That's your barrier. Apply a voltage. Electrons tunnel across the gap. The tunneling current is exponentially sensitive to the gap width. Move the tip 1 angstrom closer, the current changes dramatically. Scan the tip across a surface, measure the tunneling current, and you can map out individual atoms. Nobel Prize 1986. The Sun. Hydrogen nuclei in the Sun's core are trying to fuse. But they're positively charged, they repel each other. There's a huge electromagnetic barrier between them. The Sun's temperature gives them kinetic energy, but not enough energy to classically overcome that barrier. Solution: quantum tunneling. The nuclei tunnel through the electromagnetic barrier, get close enough for the strong nuclear force to grab them, and fusion happens. The Sun solves the barrier problem billions of times per second. Flash memory. Your USB drive traps electrons behind an insulating barrier. To write a bit, you apply a voltage that lowers the barrier just enough that electrons can tunnel through and get trapped. To erase, you reverse it and let them tunnel back out. Every time you save a file, you're exploiting the solution to the quantum barrier problem. Here's what really gets people. In the barrier problem, you never find the particle inside the barrier. The wave function exists in all 3 regions, yes. But if you tried to measure where the particle is while it's supposedly tunneling, if you stuck a detector in region 2, you'd collapse the wave function. You'd either find the particle in region 1 or region 3. Never in region 2. The particle doesn't take a little journey through the barrier. It's not drilling through or finding a gap. It exists on one side. The Schrödinger equation says its wave function extends through the barrier. And sometimes when you measure, it's on the other side. That's tunneling. It's fundamentally about probability amplitudes, not about particles traveling through space. So let me leave you with the key takeaways. First, the barrier problem is the foundational setup for understanding quantum tunneling. A particle with energy E approaches a barrier of height v theta. Classically, if E is less than v theta, it can't get through. Quantum mechanically, it can. Second, inside the barrier, the wave function decays exponentially. Most of it reflects, but some penetrates. If the barrier is thin enough, some wave amplitude makes it to the other side. Third, the transmission probability depends on barrier width, barrier height, and particle mass. Thin, low barriers and light particles mean more tunneling. Fourth, this isn't abstract theory. Scanning tunneling microscopes, nuclear fusion in the Sun, your phone's storage, all depend on solving the barrier problem. Fifth, the particle doesn't travel through the barrier. You can't catch it inside. The wave function extends through, and measurement sometimes finds the particle on the other side. That's the weirdness of quantum mechanics. The barrier problem shows us that nature obeys probabilities, not certainties. That's all for today. Take care.